there's a problem when you start thinking about nonlinear equations. I'm going to erase this. Everybody okay with that? All right. And let's talk about how to think about this method, which is, let's go back to something like this. I can still have the same boundary conditions as before. Let's say y at A is equal to alpha, y at B is equal to beta. And then I ask the question, I would like to solve this for some generic f. Now, the f here might be nonlinear. Okay? So you still do the discretization process. You still would say, okay, let's do the following. This thing here is y of point in front minus twice the current point plus point behind all over delta t squared is equal to f t, y of n plus 1 minus y of n minus 1 over 2 delta t. And I have this. And, if I multiply by delta t squared, let's call this f of n, because that's where I'm evaluating it. And so what I'm going to get is big, nonlinear system of equations. Okay. Let's talk about also the importance of x equal to b. The importance of x to b is there's a few things about it. First of all, there's a procedure you could write to do it, right? There's an algorithm that you do. And underlying there is a big assumption. Underlying there is this assumption that when you solve ax equal to b, there is one unique solution. And if there isn't, it's because that determinant of that matrix A was 0, and there's problems. But, right, as long as it's not singular, you know that when you get an answer, it is the only answer possible. Now, when you have a nonlinear system, tell me, how many solutions does it have? 31. Just kidding. You don't know. It could be 31. It could be 17. It could be 3. It could be 0. It could be infinity. That's a little bit of a problem for you, because you're going to try to solve this thing, right? And you don't know if there is a solution, if there isn't a solution. There's 17 of them. Did I find the right one? Nonlinear systems are problematic. Most of the techniques set up to solve such nonlinear systems, and this is going to be typically a huge nonlinear system, right? I'm going to discretize this thing, and I got to solve, let's suppose I discretize it into 100 points. I've got to solve 100 nonlinear equations simultaneously. Almost every method used to solve a nonlinear system relies on you giving it a guess. Okay? So nonlinear systems, the best way to solve them is being a really awesome guesser. Okay? And by the way, how would you think about solving a nonlinear system? I just want to make a couple comments about it because it's not clear we want to go into much too depth of this, except to say there are algorithms to do it. There's this f-zeros command in MATLAB that looks for zeros of a function. What's it doing? And what does it need from you? The f-zeros command typically wants you to guess the solution first. And it'll take that solution, and what it's going to do is going to iterate. Okay? There's this method called Newton method. So you guys have been using it, right? The Newton method for the practice was there. And the whole idea behind the Newton method was to say, how about, I have this function, and here's the solution. I'm trying to find, here's my function f of x. I'm trying to find when is f of x equal to 0. And there's some value, let's call it x naught. Let's call it actually something else. Let's call it x bar. There's an x bar where that's 0. And how do you find that? If it's a complicated function, oftentimes you're not going to be able to write down the solution. So what you're going to have to do is find a numerical way to find this. And this is why I had you just do a little practice problem with this. But Newton's method says, OK, guess the solution. And what Newton's method said is the way Newton's method is going to work is going to be the following. I'm going to guess a solution, x naught, and it's going to be wrong. But the way it's going to do is going to say take that solution and try to iterate towards the real solution. So the way it does it is it goes off from here, and wherever this thing is, so I picked x naught, and clearly my function is not 0 there. Here it is. This is the value. It's supposed to be up here. It's not. But what I'll do is, to get my next value, is I will take off on the tangent line. And look where I hit. This I'm going to call x1. And I ask the question, is that the solution? No, because look, here's my value, which is clearly not 0. All right, do it again. Take off on the tangent. There's x2. Is that the solution? No. Take off on the tangent. Take off on the tangent. You see what's happening there? And I keep going, and I converge to x bar. It's an iterative procedure that does the following. It says, how do I know which way to go on a guess? You give me a guess. Fine. What's the computer good at? What does it love to do? It loves to iterate. So let's just have it something to iterate on. So the way it iterates is to say, I will take off on slopes and hope that I'm heading in the right direction. This concept is the same that applies here. If you're going to solve a nonlinear system, so this Newton method is just a one-dimensional version of this. Now think about going to some higher space. What you really want to do is take off on the gradient. The gradient tells you, essentially, it's just like the slope. How do I pick a solution, I pick a guess, and it's wrong. How do I get to the next guess and the next guess and iterate forward? You do it according to the gradient. And what you hope is the gradient is pointing you in the right direction. Now, for this case here, clearly, it's a made-up example, the slopes point you to here and get you to converge. Okay? And by the way, here's a really awesome, yet completely useless theorem. Ready for it? Newton's method is guaranteed to converge if your guess is sufficiently close. Tell me what sufficiently means. Because sufficiently could mean, hey, anywhere in the ballpark of infinity, depending on the function, it converge no matter how you guess. And some of it, you better guess within 10 to the minus 6. Well, the thing's taken off on you. But it is guaranteed to converge if you are a good enough guesser. So that is how people build these routines. You say, you know what, maybe you know something. And by the way, so on a practical note, this is kind of true. A lot of these nonlinear systems, you might actually have some insight to the system. You might know how it sort of behaves. You know what you're kind of looking for. Maybe out of this whole sea of, 31 solutions, the one you want, you kind of know what it should kind of look like. And you guess that. And then you hope for the best. So, but if you don't know anything, you're just stuck. Now, although if you do have zeros, you know what it guesses? If you don't give it a guess, it just says, how about if we guess 0 is the solution? And it'll take off from there, and it will go somewhere. It might be where you want, it might not be. Okay? So nonlinear systems are difficult. And this is why there's not a nonlinear version of A \B, because you can't build it. So, but what they can guarantee you is \/ will work nicely, and here's the example of it.